At this point, we've spent the past couple of months looking at derivatives. We've defined the derivative, we've looked at different ways to calculate derivatives of functions, and we've looked at several different applications of derivatives. The last few weeks of Calculus 1 are devoted to the other fundamental of calculus, the integral. We're going to be getting into integrals in the next week or two, but before we do that, I want to look at what an antiderivative is, which is the opposite of a derivative, probably not terribly surprising by the name. And these are going to be very closely related to integrals when we get to those. Now, if you have already seen integrals before, please do not jump ahead. We're going to move at a pace assuming that you've not taken calculus before and you're seeing integrals for the first time. And so if this is something you've already seen, please don't jump ahead using the rules of integration that you've already learned. We want to build everything from the ground up. And to do that, we're going to start with an example. Suppose we are given the position function for a particle, but we want to know velocity. So I'll say that again. We're given the position function, and we want to figure out the velocity. I think you know at this point that if we have the position function, we can take the derivative to get the velocity function. So if our position function, s of t, for example, was equal to t cubed, if we wanted to know the velocity, we could differentiate that. V of t is the derivative of s of t. And we know the derivative of t cubed is 3t squared. Right? That's something that we've seen before. But what if it was the other way around? What if we knew the velocity function and we wanted to figure out the position function? Can we do that? And we should be able to, because it's just going in the other direction. If you start at a certain point and you have a certain velocity, you should be able to figure out where you've gone. And we can do that, and it's just a slightly different problem. Let's take a look at an example here. If we know that we've got a velocity function where the velocity is equal to 2t, and we want to know what the position function is, well, we know that the velocity is the derivative of the position, so we just need to find a function that has derivative equal to 2t. And I think you know what that answer is. Which function of t has a derivative of 2t? Well, the answer is t squared. So if the velocity function is 2t, then the position function could be t squared. Because this is the opposite of doing a derivative, we call this an antiderivative. Bloop. This says a function capital F, and we often use capital F to talk about the antiderivative of lowercase f, but a function capital F is called an antiderivative of lowercase f if capital F prime of x is equal to lowercase f of x. It's basically undoing a derivative, or you're doing the opposite thing. Let's look at another very similar example. Let's let a function f of x be x squared. Let's find capital F of x, which I will use to refer to the antiderivative. The capital F of x doesn't always refer to the antiderivative. You could theoretically have one function of x that was lowercase f of x, and then just use capital F of x to mean another function. So in the entire world of math and the entire world of STEM, capital F does not always mean the antiderivative. But if you're in a calculus class and you're in the portion where you're learning about antiderivatives, that's the notation that we'll often use. And so you can assume for now, if I write capital F of x, it means the antiderivative of lowercase f of x. Now, some of you might already know the answer. Some of you might not have any idea what to do. Some of you might be kind of in the middle. And one thing we know is that when we're taking the derivative, the exponent gets lower by 1. And so if we're taking the antiderivative, it should get higher by 1. So you might think maybe the antiderivative is x cubed. That might be a good first guess. But here's the thing. If we differentiate that, if we take the derivative of x cubed, that gives us 3x squared, but we want just x squared. So if we need to make 3x squared change into x squared, all we need to do is divide our function by 3. So actually, capital F of x equals x cubed over 3. Because when we differentiate that, we know that the derivative of x cubed is 3x squared, and we've got to divide that by 3, and the 3's cancel, and we get x squared. So this ends up working for the antiderivative, but that doesn't. We will pretty quickly get to the point where we have a lot of rules of taking antiderivatives, similarly to how we have rules of taking derivatives, and problems like these will become very easy after we look at a few different examples. But for the first example, I wanted to think kind of intuitively and play around. We know when we differentiate a power function, the degree goes down by 1. So for the antiderivative, it makes sense that the degree might go up by 1. So going from x squared to x cubed is a good starting point, but it doesn't give us the exact derivative we need, so we had to adjust a little bit. That's the way we're going to be thinking now. So f of x equals x cubed over 3 is an antiderivative of x squared, but I want to give you another thing to think about. Let's consider capital F of x equals x cubed over 3 plus 4. I've taken that function that we've just looked at and I've added a constant. Let's differentiate that and see what we get. We already know the derivative of x cubed over 3 is x squared. We've already done that. So the derivative of that term is x squared. Plus, what's the derivative of 4? Well, the derivative of a constant is 0. And x squared plus 0 is x squared. So that also works. X cubed over 3 plus 4 is also an antiderivative. In fact, we could have added any constant. We could have added 100, or we could have added negative 3,654. Doesn't really matter. That constant term, when we differentiate, is going to go to 0. And so when we're talking about antiderivatives, whenever we figure out a specific antiderivative, we're going to say that the general antiderivative is that quantity plus a generic constant, because we can add a constant and it doesn't change the derivative. So we have this statement: if capital F is an antiderivative of lowercase f, then the most general antiderivative of f is capital F of x plus c, where c is an arbitrary constant. So if we have, in this example, f of x equals x squared, then the general antiderivative, capital F of x, is going to be x cubed over 3 plus c, plus a constant. We write this because we don't know if the antiderivative is x cubed over 3 plus 0, or x cubed over 3 plus 8, or x cubed over 3 minus 100. All of these are antiderivatives of the original function. If we have more information, which we'll see a little bit later, we might be able to figure out what the specific antiderivative is. But when we're just calculating an antiderivative, we have to keep in mind that it's possible there is a constant term there in our antiderivative. We're going to look at some concrete examples in the next video so you can wrap your mind around this and get your hands on some of these.